Welcome to our second mini lecture on Unit 11. In this mini lecture we are going to talk about dark energy, but in order to understand about dark energy we're first going to have to talk about a specific type of exploding star called a Type 1a supernova. And you read about this before back in chapter 21, assuming you did the reading, but we didn't talk much about it then. We'll talk about it now. In chapter 26, this is where we talk about how Type 1a supernovae helped us to learn about dark energy. Now, I will warn you that dark energy is a new and rapidly changing area of astronomical science. We are on the very frontiers of what we understand about dark energy, what we know about dark energy. The information that I give you now could be very different from what we will understand in 5 or 10 years. Let's begin by reminding ourselves what a white dwarf is, because we'll find that a Type 1a supernova is the explosion of a white dwarf. So when a star like the Sun dies, it becomes a white dwarf, and a white dwarf is not a short, stout little guy from the Hobbit movies, but it's a ball of carbon and oxygen squeezed by gravity into something the size of the Earth. Now it's squeezed by gravity because the white dwarf no longer has any nuclear fusion to provide heat energy to provide an outward pressure against the inward pull of gravity. The reason that the white dwarf doesn't collapse into a black hole is because of something called degeneracy pressure, that the electrons in the white dwarf don't want to be in the same place at the same time. So if your white dwarf is small enough, then this degeneracy pressure will stop gravity and you get a nice stable dense object. However, if your white dwarf somehow gets above about 1.4 solar masses, then the pull of gravity will be too strong and degeneracy pressure will not be able to stop the pull of gravity, and gravity will squeeze the star inwards. Where can a white dwarf get extra material? Because our Sun's going to be a white dwarf about 0.6 times the mass of the Sun. This limit is 1.4 times the mass of the Sun. The Sun's white dwarf is nowhere close to being able to reach this limit. But if you make a massive white dwarf, say a white dwarf that's about 1 to 1.1 times the mass of the Sun, and it has a close companion star, it can steal material from the companion star. This process is called accretion, and the material comes over. First it forms a disk and it slowly spirals inward like a whirlpool and lands on the white dwarf. So the white dwarf will grow in size and mass over time. So what happens as a white dwarf gets close to this limit? Let's say that our 1.1 solar mass white dwarf has accreted 0.3 solar masses of material, so it's at this 1.4 solar mass limit. Well, we can use another analogy. Let's say we've got a university auditorium here for an exciting astronomy lecture, and we start filling it full of typical juvenile delinquents, such as on the left. The first people into the auditorium are going to sit in what we call the low energy seats, the ones at the back, the ones at the side, the ones that are easy to get to and you can fall asleep and don't have to pay attention. This is what a low mass white dwarf is like. But as you add more and more material, you begin to fill up all the spaces that the electrons can be at, and so you get more and more energetic electrons. They're sitting in the high energy seats, the ones that are close to the speaker, where you have to crawl over people to get in there. And this process will continue until you completely fill the auditorium, which might be at, say, 1.3 times the mass of the Sun. But let's say that I really want to give this astronomy lecture, so I hire some people to shove more and more delinquents into the auditorium. They grab people off the sidewalk, stick them in the auditorium. Soon it's standing room only and people are starting to get uncomfortable. Japanese Tokyo subway, and they have people who are hired to just shove more people into subway cars. So I hire some of those people. We keep shoving people into the auditorium. Now the fire marshal would be angry, and it gets so crowded and so hot and so uncomfortable that one of these people is going to accidentally step on the foot of the person next to them. Person whose foot gets stepped on gets mad and takes a swing at the first person who ducks, and so the guy who's swinging a punch lands it on some other poor innocent sap who then gets mad and tries to hit back and accidentally hits someone else, and pretty soon a brawl breaks out and the whole place just explodes with violence because of me putting too many people in there. Same thing happens on a white dwarf. When there's no more room for any material, when there's no more space for any electrons to go, carbon fusion begins. Remember, the star is made out of carbon and oxygen. There's no outer layers of the star to hold in the energy, so as the star heats up, the material begins to fly outwards. There's nothing to keep it in, and it just explodes outwards in a supernova. And this type of supernova is called a type 1a supernova. The type name comes from history when people didn't know what was exploding and they noticed some different characteristics. A type 1a was a specific characteristic, and we now are positive that type 1a supernovae are white dwarfs that have somehow gotten enough material from a companion star to hit this limit of 1.4 times the mass of the Sun. The carbon fusion ignites, and that blows the entire star apart. Now what you'll notice is that this means that every single type 1a supernova has basically the same thing exploding. A carbon-oxygen white dwarf that is about 1.4 times the mass of the Sun. And anytime you set off a bunch of similar detonations, you're going to get similar explosions. So here's a picture of a type 1a supernova. This one is called Tycho's supernova because it's the supernova that Tycho saw in 1572. This is a picture taken in X-rays. There's not much to see in visible light, but in X-ray light we see a lot of these fingers coming out. You notice that this supernova is almost perfectly round. The shrapnel coming out about at equal speeds at all directions. This is a characteristic of type 1a supernovae. And if we measure what these are made out of, we can see that the elements that are here are the products of carbon fusion. Since we always have the same mass and the same chemical composition, the explosions are nearly identical, as I've already said. So if they're identical explosions, this means that they will have identical luminosities. If we have identical luminosities, that means that if we can spot one of these explosions somewhere in the universe and we measure how bright it appears to be, we already know how bright it is. And just like with the Cepheids, if we know how its actual luminosity and its apparent magnitude, we can get the distance to the supernova. This is part of our distance ladder that we talked about in Minilecture 1. And supernova type 1As are among the brightest supernovae. They're nearly as bright as an entire galaxy, and that's bright enough that we can see them all the way across the universe. So we can use type 1a supernovae to measure the distances to the most distant galaxies that the Hubble Space Telescope can see. Since we can measure distances now to furthest galaxies, we can use type 1a supernovae to help us understand the history of the expanding universe. If we measure distances with type 1a supernovae, what we find is that for really distant supernovae, so these here in red on this diagram, like the Hubble diagram we saw in the previous mini lecture, on the x-axis we have this thing called z. Z is the redshift, so it's like the Doppler shift. So the x-axis here is velocity. The y-axis is a measure of distance, and so we're plotting velocity on x, distance on y. And you see, first of all, it's not a straight line like it is in the nearby universe. It curves. This curvature tells us that the Hubble constant changes over time. How fast the universe is expanding changes over time. When we look at the details, we notice the universe is now expanding faster than it used to be. And this is unexpected because if the universe started with some sort of explosion with all the galaxies moving out, gravity will try and slow the universe down and will slow the universe down. And so over time, the expansion of the universe should be getting slower and slower and slower. And this is shown by the solid blue line in the graph, what we would expect just if gravity alone were working. The blue points in the inset of the graph show, averaging over the supernovae, what the universe was actually doing, and you see it doesn't agree with that prediction. What it does agree with is the dotted black line, which is a prediction allowing for the universe to accelerate. So it appears that the universe is expanding faster now than it was in the past. Don't worry about the other lines, it's lots of other options. None of them work except for this idea that the universe is accelerating. When this was discovered, it was shocking because no one expected it. And so the discoverers of this won the Nobel Prize in 2011. So what can cause the expansion of the universe to speed up? Well, for that we need to go and talk to Einstein about what he called his biggest blunder. 2 units ago we talked about general relativity and how the theory of general relativity discusses how mass interacts with this thing called space-time, and that mass causes space-time to bend. It turns out it's not just mass causes space-time to bend, but any energy causes it to bend. Mass is one of the densest forms of energy, so it's the one that does most of the bending in today's universe. But if you had a lot of photons in one area, a lot of electricity in one area, a lot of magnetic fields in one area, that could also bend space. And any other type of energy would also distort space. When Einstein applied general relativity to the universe as a whole, he found it predicted that the universe should either be expanding or contracting. And he was surprised by this because astronomers at the time didn't know about the expanding universe. This is well before we even knew what galaxies were. Einstein said, well, I can make the universe stable, not expand and not contract, if I add an extra term in my equation. Einstein introduced a term that he called lambda, which the Greek letter lambda looks like a triangle that's missing its bottom side. And this lambda would be a property of space, sort of like an extra energy. It would keep the universe from either expanding or contracting, or depending on the value, it could make the expansion faster or slower. But of course, Einstein called this thing a cosmological constant that would keep the universe static, which is what all astronomers thought should happen at the time. Once the expanding universe was discovered by Edwin Hubble, Einstein realized that, the universe is expanding, and so he called this cosmological constant his biggest blunder and just set it equal to 0. Set it equal to 0, it's like it's not even there, and you can go ahead and you get an expanding universe. So here is Einstein's equation. It looks ugly. It's actually uglier than it looks because those R's and G's are entire matrices of numbers. So it's a hard equation, but you notice that capital lambda there, that's the one that Einstein put in, that's the one that he set equal to 0. When astronomers discovered that the rate of the universe's expansion was accelerating, they realized that this cosmological constant could explain it. If you set the value of lambda equal to something that's not equal to 0, you can get the universe to speed up over time. And that's all fine and good, but that still doesn't tell us why it's happening. It still doesn't tell us what this cosmological constant is. Everything else in nature, every other force, is something. It's caused by something. And here you have some number that Einstein never really explained where it came from. And it seems to explain the expansion of the universe, but we don't know what it is. Because Einstein's equations deal with energy, and energy can curve space, and an accelerating universe is causing extra curves to be put in space, the cosmological constant acts like some weird form of energy. And since we're in the dark as to what this energy is, astronomers have started calling it dark energy. So what are some of the options for what dark energy could be? And so what can we speculate about dark energy? There are 3 main possibilities, and I think all 3 are possible, and you could talk to different astronomers and some might favor one over the other, but there's no consensus that any one of these is better than the other. So the first possibility is that there's some new type of physics, some new type of energy, maybe some weird new particle that we never thought of that's not predicted in our current theories, maybe some new form of energy that's not predicted in our current theories. There are some people who work on these weird type of physics called string theory. String theory is trying to combine gravity with the rest of physics, and basically it's nebulous enough that you can make it do whatever you want. So some people say, oh, it's showing us that there's this thing called string theory. We don't know. We would just say some new type of physics that we don't currently have a good theory for. The second possibility may be that our understanding of gravity is wrong. So remember that Newton's gravity worked for nearly 250 years before we found that it wasn't quite right. So then Einstein came along and proposed general relativity, and that's worked for nearly 100 years. And it seems to work in all sorts of situations, but maybe it's not the last answer in what gravity is. For example, a lot of physicists think that we need to combine our theory of gravity with our theory of subatomic particles, and they call this quantum gravity. There's no good hypothesis for quantum gravity yet, no good understanding of it. Maybe when you come up with it, dark energy is something that would pop out. Maybe general relativity and/or gravity breaks down on large distances. We know of no reason why it should, but maybe it does. So perhaps our understanding of gravity is wrong. The third possibility, and this is an intriguing one, is that maybe we've been solving general relativity incorrectly. Those equations that Einstein came up with, you cannot solve them with pencil and paper. You have to use some sort of approximation. So Einstein's general theory of relativity is based on the assumption that the universe is pretty much the same in every single direction. We'll be talking about this in the next mini lecture. It's something called the cosmological principle. But we know the universe isn't exactly the same in every direction. I mean, looking in front of me, I see a desk in one direction, a wall in another direction, a window outdoors in another way. But if I look on big enough scales, like if I looked out into the universe, I would see galaxies and stars pretty much in every direction that I looked. And so we've always just assumed that the small scale differences don't matter, and only the large scale differences do, but maybe the small scale ones do. We don't know. We don't have any way of solving this, but supercomputers may be able to help. So what we do know is that dark energy, whatever it is currently dominating the universe on large scales. When we look on large scales, if we assume that it's some form of energy and that Einstein's equations are solved correctly, we find that somewhere around 70 to 75% of the entire universe is dark energy, is the stuff that we have no clue what it is. Another 21% of the universe is dark matter. Now, we already talked about dark matter. We're not quite sure what it is. We have a favored hypothesis, but it's not proven yet. And only 4% of the universe is the ordinary matter, atoms and electrons, molecules, what we're made out of, people, hamsters, planets. That's stars. Galaxies are only 4% of the entire universe. And the rest is steeped in ignorance. But that's good, because that provides us science. That gives us something where we can go and study and make ideas and see if they're right and learn more about the universe than we ever thought we could before. So this completes our mini lecture on dark energy. We discovered it by using our distance ladder, that the most distant objects in the universe, which we can measure their distances using type 1a supernovae, and when we measure their distances, we find that the universe is expanding faster now than it was in the past. The only explanation we have for this right now is that Einstein's equations have some sort of extra term in them. What Einstein called his cosmological constant, what we will call dark energy, because that's what you throw into Einstein's equations, are forms of energy, dark because we're in the dark about it. But whatever this dark energy is, it makes up 75% of our current universe. 3/4 of our universe is stuff that we have no clue what it is. So stay tuned, because hopefully we will learn much more about dark energy in the coming years and we won't be in the dark quite so long.